Okay, so here in my second part of this matrices, I am going to look at, I'm going to put my face in the source of the energy of the sun, the Surya, or the Tejo element. And we're going to explore from here um, how does a variable move? I mean, we already defined what moves, and we defined what makes that variable move. Now let's look at the concept of motion itself. What is flow? The idea of flow is motion of anything in time. So again, let's start from the earth. When a body is moving, let's say a rock is rolling, that mass has a certain velocity in meters per second. So the motion of bodies is known as velocity, and we know that when a mass has a certain velocity, there is an amount of motion, or we call it a momentum. So these are concepts that we also explore in mechanics: momentum, mass times velocity. What happens with the motion of water? With the motion of water, it's the same thing. You know, an amount of water, let's say a volume of water is moving, and the volume was cubic meters. So we divide that by time, and we have the amount of water that flows per second or in a unit of time. So the flow of water in a tap, the flow of air, an amount of air, let's make an invisible here amount of air, a certain volume of air moving in time creates a flow of air, or a wind, right? Wind, which could be measured in cubic meters per second, the air that is moving in time. So this idea of motion applied to bodies and also to charges, when we have a positive charge or a negative charge, either way, that is moving in time, we call that a current. And that flow of charge, which is the charge over the time, is known as the amperes. The current in a circuit is the ampere. And when we explore the motion of heat coming from the sun, we're looking at energy in joules coming from the sun in a certain amount of time. And this is already the concept of power. In this case, it is solar power. That means the amount of heat that reaches the sun every second, and the unit for power is watts. So these are the concept of motion in time. It's interesting to know that the solar power, the amount of energy that reaches the earth in 1 hour, is enough to provide the energy that we need to live as a planet for a year. So the amount of power reaching the earth is huge. Only reaching the earth, I'm not saying coming out of the sun. The amount of power coming out of the sun every second is enormous. We can explore that later on. So this is the concept of motion in time. So let's look a little bit deeper into the concept of energy. We explored only the energy that comes from the sun. Now let's explore other forms of energy, like let's look at gravitational potential energy, right, in joules. What do we need to have gravitational potential energy? Well, we need to have an apple at a certain height, right? So the multiplication of the weight of the apple, mg, times the height of the apple will give us the amount of gravitational potential energy that then could be transformed into kinetic energy. And we saw this equation before, right? So transformation of gravitational potential energy, energy of position, could be in the form of kinetic energy. What happens with the energy of water? How do we have hydraulic energy? To have hydraulic energy, we need to trap an amount of water in a dam, for instance, a volume of water in a dam, and then make that volume of water push a turbine. So this could be a turbine, and that transforms, again, gravitational potential energy into kinetic energy. So we could say, again, it could be the mass times gravity times the change of height or it could be a certain volume of water at a certain difference of pressure, because we saw also that the water can go upwards, like from the heart to the head, blood flows because of that pressure. So there is hydraulic energy when there is a volume of water at a certain pressure. We call this energy, again, hydraulic. And this is mechanical. Now, what happens with the energy from the air? We have wind energy, right? Energy that can turn a windmill, or wind power if you want. Or we could store energy in a tank. So if we have a certain volume of air, right, stored at a certain pressure in pascales, then we say we have some kind of aeolic energy, or energy stored, like for instance those machines that work with pneumatic energy. We also call it pneumatic energy. Pneumatic energy. They store pressure, a volume of air at high pressure, and that energy that is stored can push a tool, for instance, to break a road. We call that also aeolic, energy from the wind. Well, the energy from the stars, from the sun, we saw, and we call that solar energy directly. No conflict with that. And to have electric energy, we need to have two things. We need to have a charge, and we need to have also a difference of potential. That means a battery, and this is known as Joule's law. This is known as volt times Coulomb is joules. This is known as electric energy. So electric energy is stored in a circuit, for example. So basically, to understand energy, we need to understand two things. Something moves and something pushes, and we need to have both of them in any form of energy. Right here, we need to have photons, and we need to have a difference of temperature that pushes them away. Here, we need to have a volume of air, and we need to have a difference of pressure that pushes the volume of air. Same thing with the volume of water. Same thing with an apple or a stone that needs to be pushed by some force. In this case, it could be the force of gravity, or it could be the work done by any force to push any stone. So that's a very important concept in physics, the concept of energy. Interesting is we talked about different forms of energy, but we need to understand that energy is one single concept. So there is one energy in this universe, and that energy became matter, and that energy became gravitational potential, becomes solar energy, nuclear energy. One energy comes with different costumes, but it's one energy, and we measure it in joules. Important to remember that. And once we understand the concept of energy, we can explore the concept of power. Power. What is power? What makes power? By definition, power is energy divided by time, or rate of work. So if we're looking for formulas for power, we could look at mechanical power. Mechanical power in the earth. When do we have mechanical power? When we do a lot of work, mechanical work in time, right? And we said that to do mechanical work, we need forces to push a certain distance over time. And we saw that distance over time is velocity. So there are two factors that make mechanical power. One is force, and the other one is velocity. We can play with these factors. We can, for example, in a bicycle, we could play with a gear system to increase the force, sacrificing velocity, but we cannot increase the power. We only have a limited amount of chemical energy that we can put into, or mechanical energy that we can put into a bicycle. So if we use the first gear, we have a lot of force, but less velocity. If we use the fifth gear, we can do more velocity, but less force. So this is used when we go downslope, and first gear when we go up the hill to increase the force. Basically, there are two factors for power on air. Now, when we look at the power in the fluids, I'm going to treat both of these fluids together because it's the same formula. Remember that energy is pressure times flow, right? Sorry, pressure times volume. And when we do pressure times volume, which is energy, divided by time, we find the formula for power as pressure times flow. And this is also something interesting. It explains many things. We can increase the pressure by sacrificing the flow and vice versa. This has to do with the shape of wings, for example. When the air passes on top of the wing, it has to go a larger, I mean, two molecules of air that are crossed by a wing will have to move a different amount of distance. Like the one that is on the top will move the more distance, therefore they move faster. And if they move faster, they lose pressure. So somehow we could explain this force, this upthrust. Why does a plane fly? It has to do with the concept of power in fluids. We can explore that later on. I don't want to go too much into the details now. We saw solar power. Solar power is directly energy coming from the sun. So the solar power is the energy over time, just the definition of energy in watts. And when we learn the electrical power, when we look at electrical power, we're looking at two concepts. Remember, energy, which was charge multiplied by voltage over time, but charge over time was current. So there are two factors for electrical power. One is the current and the other one is the voltage. We will explore these two factors when we study in more detail electricity, but it's the same principle. You can play with these two factors to transform electrical power to high voltage and low current, or high current and low voltage. Very important concepts to explain many things that we do in physics, like, for example, transmitting electrical power from one part of the Earth to another part of the Earth in high voltage systems. Or, for example, what we do when we change the gears in a car or in the bicycle, or even when we are running a long race or a short race, how we play with these two factors that make power. These are the laws that make power. And there is one more concept, or two more concepts, I should say. The concept of resistance. You know, if something moves, there should be a path. There should be a path for bodies to move, for air and water to move, for sunlight to move. A path that means what allows, but also opposes to that motion. And that is the definition of resistance, the ability to absorb, what allows and restricts or opposes to the flow of motion. So when we look at resistance on Earth, what makes a body roll on Earth, like what makes a car or a bicycle or even our own bodies to move forward on Earth, is the concept of friction. So we explore this concept in mechanics. When we look at fluids, remember, these two are fluids. So we look at pipes. For example, we could think about, we could think about a water tap as a variable resistor for liquids, or we could think about the nostrils for our own breathing systems, nostrils. They allow, but also oppose. If the nostrils are covered, then the resistance is too high and there is no flow, there is no power, there is no wind power flowing into, air power flowing into our body. So nostrils need to be clean. And the tab, like a variable resistor, a pipe, any pipe represents a restriction that allows the water to go through, or even gases, gas pipes, water pipes. So this is something that is very important in buildings, for instance. And also in our system. If we think about our system, the water pipes in our body are the veins, the arteries, the water pipes, the air pipes are the nostrils, the trachea, the alveoli, all these tiny, tiny pipes that allow the air to go into the lungs and diffuse. So pipes are essential, pipes for the neck also. What allows and opposes to the flow of charge? Let's look at this first. Charge is moving through wires or lamps, and we call these resistances. We measure them in ohms, we shall study them. A lamp is a resistance, a wire is a resistance. Anything that allows the electrons to move along are called resistances. And when we look at the sun, how the energy of the sun reaches the earth, we have to identify at least 3 different resistances to the flow of light coming from the sun, right? Or heat coming from the sun. So if it's going through fluids like, okay, let's go through space first. If it's going through space, here, there is nothing, right? There is just rays of light traveling through space at the speed of light. We call that radiation. So transfer of heat through space is what we call radiation. Now, if it goes through fluids, if it goes through water or air, through the atmosphere, then we call that convection. And if it goes through matter, let's say solids like Earth, solid matter, like heat coming from the Earth to our body by vibration of molecule, from molecule to molecule, we call that conduction. So basically, when we study the ways in which heat is transferred, we study radiation, convection, and conduction. The last concept in this first matrix for holistic understanding of physics has to do with the concept of capacitance, the ability to absorb, retain, and release. So we already know what is a capacitor, a lung. A lung is a natural capacitor in our body because it absorbs, it retains, and it releases the energy that comes from the air. Volumes of air are trapped in our lungs, right? Let's use a different color for capacitor. So this is a lung. It absorbs, retains, and releases energy from the air. We could define the lung capacitance as how much volume is absorbed by changing the pressure per unit of pressure. This is a definition of lung capacitance. If you can absorb large volumes of air, you're expanding your lungs, you're breathing properly, then you have a big lung capacity. It is said that we only use 30% of our lung capacity, and I believe that is true. What happens with the Earth? When we study the Earth, let me mark a boundary here for the Earth. When we study the Earth, here, oh, there you go. When we study the Earth, the ability to store, for example, a weight, we want to store some kind of load. So here we hang a load in newtons, and the spring stretches. When we look at the ability to absorb, retain, and release energy, we're looking at the concept of elasticity in physics. And we know already Hooke's constant, the amount of weight that you can put on a spring to see how much it stretches, how much load is extending the spring. This is known as Hooke's law. And it explains the concept of elasticity or capacitance. In our bodies, we have natural capacitors in the muscles, right? Muscles are elastic capacitors. They carry weight and absorb and, and release energy. In the case of the water, when we try to look at the capacitance of water, the amount of volume that we can change, I mean, we cannot compress water. It's very low. The ability to compress water is very low. So there is a very low capacitance. Water is very good for transmission. That's why the blood transmits and the lungs absorb and retain, because capacitance is associated with the concept of compressibility, and water has very low compressibility. We cannot compress liquids, right? Very little compressibility. Solids also have very low compressibility, but we can make elastics and increase the compressibility of solids. What about the capacitance for solar energy? Okay, solar energy, I'm going to mark it in red, has every object that receives solar energy. So if I have any mass here, for example, I have a mass of water or a mass of a certain rock, the amount of energy that that mass absorbs, that means per unit mass, over the increase of temperature, that is what we call the capacitance. So for instance, if we look at the capacitance of water, water has a capacitance of 4200 joules per kilogram Kelvin. And if we look at the capacity of sand, sand has a capacity of probably 100 joules per kilogram Kelvin. So that means that water needs a lot of energy to increase the temperature by 1 degree, 4,200 joules, while the sand, with a little bit of energy, immediately increases the temperature by 1 degree. So the capacitance is giving us an idea of how well the energy gets stored. And this is why the water in the air is so important, because it is a greenhouse gas. The water, the humidity in the air absorbs the heat during the day and releases slowly during the night. So water in the air, clouds, are very good for balancing the weather and giving us low thermal amplitude, right? Low thermal amplitude. If you're in the desert, the air is dry and the capacitance of the air is very low, so it gets hot and then it gets cold. So at night it's freezing and during the day it's burning. So those clouds that during the day give us shade, at night act as blankets, they give us warmth. Very, very, very beautiful balance in nature. So the concept of specific heat capacity is something that we're going to explore when we study heat, at least conceptually. And there is one more concept that we will explore when we study electricity, and that is the idea of an electric capacitor. Some of you might know what this is. It's like a tank. It is normally symbolized like this, a tank that stores charge, positive on one side, negative on the other side. So it is the same as a lung, but in this case what gets stored is charge, capacitor. What is a capacitor in electricity? The amount of charge that you store per unit voltage. That is what we call 1 Faraday, and it's the capacitance of a capacitor, an electric capacitor. So these are the concepts that we study in physics: capacitance, resistance, energy, motion, potential difference, variable. It's not much, that's all. If you understand that and you understand the laws of physics, you understand everything. You just have to play with these formulas and solve some problems. Meditate on that.